Hello everyone, this is Sir Aris. Today we will talk about differential equations with discontinuous forcing functions and also impulse functions. Let's have an example. Find the solution of the differential equation. Here, 2y double prime plus y prime plus 2y equals gt, where g is given by u, the step function at 5t minus u20t can be written like this: so 1 from 5 to 20, 0 otherwise. Assume that the initial conditions are u at 0 is 0, and or y 0 is 0, and y prime 0 is 0. Taking the Laplace transform of this equation, you get this, and we use these formulas. Um, we set Laplace transforms of y as capital letter ys, so this is ys. Y prime is given by this expression, sys minus y0. Y double prime is this, and for g is given by u5 minus u20. uh, Laplace transform is linear, so we can uh, distribute this L. So by definition, that's simply e to the minus 5 Laplace transform of the function, which is just the function multiplied to u, which is just 1. So this is 1 over s. And also, this initial conditions, y0, would make this as 0. Okay, so we can simply write this expression. So that's 2 ly double prime times s squared ys, this one, plus ly prime is this s ys, plus 2 ys equals this e to the minus 5s minus e to the minus 20s divided by s. Or we can write it as ys times 2s squared plus s plus 2 equals e to the minus 5s minus e to the minus 20s over s. So ys is simply e to the minus 5s plus e to the minus 20s, 1 over s times 2s squared plus s plus 2. We can also write ys like this. So you have hs is given by this expression, or this part, and this. So from a theorem we learned in the previous section, if we know the Laplace transform of this as h small letter h t, or inverse Laplace, the inverse transform of y is just this step function h t minus 5, and here it's t minus 20. So our goal now then is to just find for this h t. We can use the method of partial fractions. So I'm calling it method of partial fractions because we are trying to determine um, this this expression for hs um, in a form 1 over s, or let's say we don't know the coefficient, let's call it a for s, plus this, which would be a second order, so we need bs plus c over 2s squared plus s plus 2. Okay, this one is 2. Okay, combining these two, you have a 2s squared plus s plus 2 plus this times s bs plus c divided by s 2s squared plus s plus 2. Okay, so you have a times 2as squared plus as plus 2a plus s squared b plus SC over S2S squared plus S plus 2. Or that's also, you can combine 2A and B. It's 2A plus B, S squared, SAS and SC. So it's A plus C, S plus 2A all over S2S squared plus S plus 2. And remember, this should be equal to this, so that's 1 over S2S squared plus S plus 2. So which means that this numerator should be equal to the numerator here, or 1 equals 2A plus B S squared plus A plus C S plus 2A. S squared and S being linearly independent, so this should be equal to 1, the 1 here. This is 0, and this is 0. So it's like having 1 times 0s squared plus 0s plus 1. So this is equivalent to this, which is 0. This 2a equals 1 gives us a equals 1 half. This 2a equals plus b makes it b equals negative 1. And if a is 1 half, then c equals negative 1 half. Okay, so when we have those values, we can then go back to this form for our hs is 1 half s minus s plus 1 half. So there's a b plus c here, but I'm writing the negative here. 2s squared plus s plus 2. Okay, and this can also be written as 1 half over s minus um, s plus 1 half. Let's factor out this 2 here. So you have 2 s squared plus 1 half s plus 1 half. Okay, and let's rewrite it again. So 1 half s minus, factor out 1 half. This 1 half, let's break into two parts. 1/4 plus 1/4 divided by this. Our goal is to create a square, so we complete the square. We already have 1 half s. So the third term here should be something like um, a square of something that if you multiply by 2 becomes 1 half. So it should be, if you multiply 1/4 by 2, that's 1 half. So the square is 1 over 16. That's 1 over 16. So we're just adding nothing, but um, that should be able to give us something here. Oh, by the way, this 2 here, this should not be 1 half. That's just 1. This is also just 1. Okay, so 1 half over s minus 1 half of s plus 1/4 plus 1/4 over, so this is s plus 1/4 squared. This is minus 1 over 16. This can be written as 16 over 16. So that's plus 15 over 16. You can take the square root of this so that you have a nicer form. So hs is 1 half over s minus 1 half of, let's separate this, s plus 1/4. So s plus 1/4 over s plus 1/4 squared plus, let's say, square root of 15 over 4 squared plus 1 over square root of 15. The square root of 15 is so that we can write this as square root of 15 over 4 over s plus 1/4 squared plus square root of 15 over 4 squared. So we can use the formulas. First is this. ECT times FT is the inverse Laplace of s minus c. So we can make use of this expression because we have s plus 1/4 with c equal to negative 1/4 here. So for this term here, there's e to the power of minus 1/4 t. For here, we can use that this here. And then once we have those s plus s minus c covered, we can just think of this as just one term s, and then we use this two. Okay, so for s, the first term is cosine, the second term would be a sine. So h then, or small letter h, is 1/2 times 1 minus 1/2 of e to the minus 1/4 over t. Let's call that t over 4 times cosine of um, this is our a, so square root of 15 over 4 t plus 1 over square root of 15 sine of square root of 15 over 4 t. And remember that our y is u5t ht minus 5 minus u20t ht minus 20. So we just set this ht to t minus 5 and t minus 20. You can write the solution. Um, if we plot the solution, you give us this plot. Take note of the discontinuities. This is at 5 here. There's a discontinuity at 20, or that's 20 here. Okay, let's proceed. Let's consider differential equations of this form where gt is large over a short interval between t naught minus tau and t naught plus tau for some tau greater than 0, and outside this interval the value of g is 0. In a mechanical system, gt is a force, and the integral I is called the impulse of the force over the this time interval defined by this integral. Since g is 0 outside the interval, we can also write overall. So overall values of t, that's just the same. Suppose t naught is 0 and gt is given by this expression. Okay, so 1 over 2 tau when it is not 0 and 0 otherwise, where tau is a small positive constant. So if we create a plot of this, suppose this is our gt, which is dt, or 1 over 2 tau between time, let's say this is a time tau, and or minus tau, this is a time uh, tau. So the value is 1 over 2 tau between this interval, but it's 0 outside. Okay, the integral of let's call it the integral tau equals the integral of gt is just the area. So that would be this length here is 2 tau. The height is 1 over 2 tau. That's just 1. Now suppose the forcing function acts over shorter and shorter, so we make this shorter and shorter. We require tau to be 0 from the right side. In this case, we obtain the limit d tau, it would become 0. But I tau is 1 for each tau not equal to 0, so it follows that I is equal to 1. We define an impulse function delta as a function that imparts an impulse of magnitude 1 at t equals 0, but 0 for all values of t other than 0. this function has these properties. So delta tau is 0 for t not equal to 0, and the integral is 1. It's called the Dirac delta function, given by this with these properties, or Dirac delta function with these properties. But if you have an arbitrary point t equals t naught, then the properties of the delta function would just follow like this. Let us try to determine the Laplace transform of the Dirac delta function. So this is the delta function. Our Laplace transform can be determined by using a limiting condition here. So we'll just solve first for this. Okay, so Laplace transform of the tau t minus t0, by definition, it's simply integral from 0 to infinity of e to the minus st d tau t minus t sub 0. Okay, but this here is not, it's 0 or non-zero only at some interval, so we can write t naught minus tau t naught plus tau of e minus st d tau t minus t naught. Now we use our simple form for the tau, 1 over 2 tau for the interval t minus tau t naught minus tau. So our L d tau t minus t naught would become t naught minus tau t naught plus tau of e minus st 1 over 2 tau dt. So this becomes negative 1 over 2 tau, or the negative comes from this 1 over s, negative 1 over s. So e minus st evaluated from t naught minus tau and t naught plus tau. So this becomes 1 over a negative 1 over 2s, 2 tau s, e to the minus s t naught plus tau minus e to the minus s t naught minus tau. We can flip this to get rid of the negative sign. So we have e to the minus s t naught. We can factorize s minus t naught. So e to the minus times minus here, it's positive. So s tau minus e negative s tau. Okay, that's our form for this. Now remember that we need to take the limit to get L. So L, our Laplace of delta t minus t naught equals the limit as tau approaches 0 positive of this Laplace transform of the tau t minus t naught. Okay, so we take the limit as tau approaches 0 plus of 1 over 2 tau s e to the minus s t naught e s tau minus e minus s tau. So if you set this to 0, is 0, this is 0, 0, so this is 1 minus 1, that's 0, so that's indeterminate, so we use L'Hopital's rule. Okay, from L'Hopital's rule, The limit is just equivalent to if you take the derivative of the numerator and the derivative of the denominator with respect to tau. This is just 2s, so you have e minus s t naught over 2s. So take the derivative of this, that's s e s tau plus s e minus s tau, and then set tau to 0. This is s plus s, so you have e minus s t naught 2s s plus s, and that gives us the Laplace transform of the delta function is e to the minus s t sub 0. Okay. Um, let's solve. I have enough space here, but we'll go to the next page. The Try to determine the integral of the product of delta function and any continuous function. Say the function is f, like here. We use our formula or our expression for d tau. That's 1 over 2 tau. That we have here 1 over 2 tau of integral from t naught minus tau t naught plus tau of f. We know to get the expression, or to get an expression for this, we can use the mean value theorem. So the mean value theorem states that f is continuous and a closed interval and differentiable. There's a number c in that interval such that f prime c is fb minus fa over b minus a. So suppose, okay, I will not prove this, but I will use it. Suppose, let's say ft, or the integral of ft dt, is capital letter ft. That's an indefinite integral. We would set the limits, or for this case, f prime of t is equal to ft. Now, if you have limits a, b, ft, dt, this becomes fb minus fa. Okay. Now, suppose we want to use this. So you have f uh, for the function capital letter f. Okay, this function here. So f prime of c would be equal to f of b minus f of a over b minus a, so that f prime c, or b minus a of f prime c, is equal to fb minus f a. Now fb minus fa is this integral. Okay, that would be our integral ft dt. You have b minus a, but f prime of c, remember f prime of t is ft, so this is c. So this we can use for this expression. Okay, we just need b minus a, so this is b minus a, and then let's call c, this tc here is a number between t naught minus tau and t naught plus tau. So this minus this, the t naughts cancel, so you have 2 tau here, 2 tau cancel here, so we are left eventually with ftc. But as tau approaches 0, this tc would approach t sub 0, so we get this expression. Now, finally, let's have an example. The form is similar to the previous example, but we have this forcing function delta. Um, if you take the Laplace transform, as usual, we get this. We have a final expression, so the Laplace transform of delta t minus 5 is e to the minus 5s. So we have this expression. We can take the inverse Laplace transform of this. Okay, so that's the inverse. We take the inverse Laplace transform here. There's a plus s plus 1/4, so we can make use of e to the minus t over 4 here. And then this becomes, if we add a square root of 15 over 4 times 4 over square root of 15, we can have that form for our Laplace transform of, or inverse Laplace transform, or Laplace transform of sine. So that if we multiply this times this, our original form, take the inverse Laplace, you get the unit step function. Okay, and then you replace the t's that you get here with t minus 5. And it can also be written like this: for 0 for t less than 5, and this expression without the u5 at t greater or equal to 5. So it activates, so the solution is 0 here, and it only activates at 5. So you can think of this as something like, so you have a phenomenon happening, but it only gets triggered at time t equals 5, like this expression, or like this plot here.